You are wrong if you think time is the same for everyone. This is a fundamental, almost instinctual belief that we all carry around in our heads. We imagine a grand universal clock ticking away the seconds, minutes, hours, for every single person, every planet, and every galaxy in perfect synchrony. That idea is not just incorrect, it is a profound misunderstanding of the very fabric of reality. This old-fashioned notion of absolute time is holding you back. It prevents you from seeing the universe for what it truly is, a dynamic, flexible, utterly wondrous place where the rules are far stranger and more beautiful than you might imagine. After you read this, I promise you will see time and space with new, enlightened eyes. The concepts that once seemed like the domain of esoteric physics will become clear and intuitive. You will finally grasp why a GPS navigator can pinpoint your location with astonishing accuracy, a feat that depends entirely on Einstein's revolutionary insights. You will understand the logic behind the famous story of twins who age at different rates, a scenario that is not science fiction, but a direct consequence of the laws of nature. This is not complicated. Before we can dive into the mind-bending consequences of relativity, we must first understand its foundational pillar, the one unbreakable rule upon which everything else is built. This rule is simple to state, but profound in its implications. The speed of light in a vacuum is constant for all observers. It doesn't matter how fast you are moving, where you are, or in what direction you are headed. If you measure the speed of a beam of light, you will always get the same number, approximately 299,792 kilometers per second. This isn't just a suggestion, it's the supreme law of the cosmos, a cosmic speed limit that nothing with mass can ever reach or exceed. This idea completely shatters our everyday intuition. Imagine you are driving down a highway at 100 kilometers per hour. A car in the next lane is moving in the same direction at 120 kilometers per hour. From your perspective, that car is pulling away from you at only 20 kilometers per hour. Now picture yourself in a spaceship traveling at half the speed of light. You shine a laser beam forward. You might instinctively think that an observer on a stationary planet would see that light beam moving at your speed, plus the speed of light. But they don't. They see it moving at the exact same speed of light as you do. Let's start with a new way of thinking. Stop imagining space and time as two separate things. They are not. They are woven together into a single unified continuum, a four-dimensional fabric. Scientists have a name for this fabric: spacetime. Don't let the word intimidate you. It's just a label for the stage upon which all events unfold. For our purposes, imagine a vast, flexible cosmic blanket. Every object, every person, every planet, every star, all exist on this single continuous sheet. You and I are not just moving through space. We are traveling through space-time together right now. Now, here is where things get interesting. Your motion through space affects your journey through time. Think of it like this. Every object has a certain amount of motion through space-time. If you're sitting perfectly still on your couch, all your motion goes into the time dimension. But the moment you start moving through space, walking, driving, flying in a rocket, you divert some of that motion from time into space. As a result, your journey through time slows down. You might be thinking that these ideas about slowing clocks and flexible time are fascinating, but have no bearing on your daily life. You would be mistaken. Every single time you use a GPS app on your phone to find the nearest coffee shop or navigate through traffic, you are directly benefiting from Einstein's theory of relativity. Without his insights, your GPS would be rendered utterly useless, accumulating errors so rapidly that it would guide you into a field miles away from your actual destination. This technology is a daily practical demonstration of relativity in action, working silently in the background of our modern world. Here's how it works. The Global Positioning System is a network of about 31 satellites orbiting the Earth at high altitudes at high speeds. To pinpoint your location, your phone's receiver needs to get incredibly precise time signals from at least 4 of these satellites. By calculating the tiny differences in the arrival times of these signals, your device can triangulate its position on the planet's surface. The system requires timing accuracy down to a few nanoseconds, billionths of a second. To truly visualize the power of time dilation, physicists love to use a famous thought experiment known as the twin paradox. It's a story that beautifully illustrates how motion through space dramatically affects the passage of time. Imagine two identical twins, Stella Terra. On their 30th birthday, Stella embarks on an extraordinary journey boarding a futuristic spaceship that can travel at 99% of the speed of light. Her destination is a star system 10 light-years away. Terra, meanwhile, remains on Earth, living her life, pursuing her career, waiting for her sister's return. From Terra's perspective on Earth, Stella's round trip takes just over 20 years. Stella travels 10 light-years out, and 10 light-years back at nearly the speed of light. When Stella's spaceship finally lands, Terra is 50 years old, with graying hair and 2 decades of life experiences behind her. The slowing of time is only one half of the strange magic motion conjures in spacetime. Einstein realized if time must flex to keep light speed constant, space must flex too. This is length contraction. A fast-moving object appears shorter along its motion. Motion slows time, and motion compresses space. Time and space dance together. When one changes, the other responds. Stella's spaceship, 99% of light speed. From Terra on Earth, the ship looks squashed front to back. Not thinner, shorter nose to tail. Inside, Stella sees normal length. Her ruler's unchanged, proper length intact. Outside, the universe rushes past. Distances to the star look much shorter than Terra's 10 light-years. Space contracts ahead of her, so the trip takes 3 years for Stella. Her clock ticks slower, and the distance she must cover is shorter. Time dilation, length contraction. They combine so both agree on the speed of light. Now we must take another giant leap, moving from special relativity to Einstein's masterpiece, general relativity. This theory completely redefines our concept of gravity. For centuries, we followed Isaac Newton's idea that gravity was an invisible, instantaneous force, a mysterious pull that massive objects exerted on each other across empty space. Einstein proposed something far more elegant and profound. He said that gravity is not a force at all. Instead, gravity is the effect we observe when massive objects warp the fabric of space-time. Picture space-time as a giant, stretched rubber blanket. Place a small marble on the flat sheet. It stays put. Now put a heavy bowling ball in the center of the blanket. The bowling ball's mass creates a deep depression, a curve in the fabric. Roll the small marble nearby. It no longer goes straight. It follows the curve, spiraling inward as if being pulled. The sun is not pulling the Earth. The sun is warping space-time. The Earth is following the straightest possible path through that curved space-time. This new picture explained things Newton couldn't. Astronomers had long known Mercury's orbit had a slight wobble that couldn't be explained. When Einstein applied general relativity, it predicted Mercury's strange orbit exactly. Warped space-time affects everything that travels through it, even light. If a bowling ball on a rubber sheet represents the sun's gravity, what happens when you have an object with truly immense mass concentrated in an infinitesimally small point? The answer is a black hole, the most extreme and fascinating prediction of general relativity. A black hole is a region of space-time where gravity is so incredibly strong that the curvature becomes essentially infinite. The depression in our cosmic blanket is so deep that it becomes a bottomless pit. Nothing, not even light, the fastest thing in the universe, can travel fast enough to escape once it crosses a certain boundary. That boundary is the event horizon. It's not a surface you can touch. It's simply where escape velocity exceeds the speed of light. Anything that crosses the event horizon, a star, a planet, an unlucky astronaut, is drawn inward toward the singularity, a point of infinite density. Near a black hole, general relativity is magnified to an unimaginable degree. Time dilation becomes extreme. From a safe distance, a falling clock appears to tick slower and slower, eventually seeming to freeze at the event horizon, never quite crossing it. These ideas might sound wild and counterintuitive. Slowing clocks, shrinking distances, gravity as curved spacetime. But they have been tested and verified time and time again for over a century. Scientists have measured them in particle accelerators, confirmed them with atomic clocks, and observed them in the majestic motions of stars and galaxies. You don't need to be a physicist with a blackboard full of equations to appreciate the core truth. The simple pictures we've discussed, the cosmic blanket, the traveling twin, the GPS satellite, give you the essential keys to understanding this new and more accurate map of reality. Einstein gave us a profound gift. He replaced the old, static, clockwork universe of Newton with a new one that is alive, dynamic, and organic. His theories show us a cosmos where space and time are not a rigid stage but active participants in the cosmic drama. They bend, they stretch, they react to the presence of matter and energy. They conspire to make the clock on a speeding rocket tick differently from the one on your wrist. This is the simple, elegant, and beautiful heart of relativity. It helps these ideas reach more people who are ready to see the universe with new eyes.